All right, let's see if we can wrap our brains around a velocity problem here to really give us some insights into the calculus that we're going to be dealing with. So let's say we have this purple line here, and the x-axis is representing hours, and the y-axis is representing distance. So this is really a graph representing someone driving in a vehicle down the freeway over a period of time. And this curve, although we don't know that this is the curve that we're actually dealing with yet, this curve represents the distance over time that vehicle was going. Okay. But let's say we did take two measurements, right? Maybe we're a passenger in that vehicle, and right at the end of 1 hour, we marked that, oh, we have traveled 45 miles. So we have the point 145, meaning in 1 hour, we have gone 45 miles. So we kind of wrote that down in a notebook. So we took a data point right there. And then at the end of the second hour, we took note again and said, oh, at the end of 2 hours, we have now traveled a total of 105 miles. Okay, so notice that these 2 points lie on this curve. That for this problem, we don't actually know this purple curve, but they are 2 points that lie on that line. Now, we would like to gain information about the total drive from the data that we have collected, but we only have 2 data points over a 2-hour period, so we're pretty limited in the amount of assumptions and information that we can gather, but we can at least get a start on things. So let's say we want to figure out what our average rate of change was from the end of hour 1 to the end of hour 2. So essentially between our 2 points here, what was our average rate of change? Okay, well, remember rate of change, right? Remember back to algebra, when we talk about rate of change, we're generally talking about slope. So it kind of makes us think, oh, are we talking about the slope of the line that would go through these 2 points? And the answer is yes, that's exactly right. So if we take a look at this and graph the line that goes through there, the slope of that line represents the average rate of change from the end of hour 1 to the end of hour 2. One question is, where did that line come from? How did you come up with that? We're going to go over that in just a minute. So I'll show you exactly how to find this secant line. The slope of that secant line gives us our rate of change. That's going to tell us our average rate of change from between these 2 points. All right, so let's remind ourselves how to find the secant line that goes through the 2 points we were just looking at. So here we've got our points. That's 145 and 105. So you just apply the slope formula to it. So rise over run. So we get 105 minus 45 over 2, right? So it's just our x1, y1, x2, y2, and we plug them right into that slope formula. We end up with 60 over 1, which is an integer. So that's 60 miles an hour. So the slope is our rate of change. Our rate of change of position is 60 miles per hour. So remember about that rate of change, right? Now, in this class, we'll be a little bit loose with calling things speed or velocity. Many of you have already taken physics classes, so you know that technically there's a difference between speed and velocity. But for most of what we do in here, we're not going to have to worry about that too much. We can kind of be a little bit loose with how we use those terms. But that rate of change and the slope is what's really important here. We measured our slope. That gave us the rate of change. Well, so what is the rate of change? Well, what our graph was representing was position. So the rate of change of position is speed or velocity, right? If you have a direction to it. So basically what we did was we were able to figure out our average speed over this time. Rate of change is 60 miles an hour, so that's our slope. Remember, if we're solving for the equation of a line, we need 2 things. We need the slope and we need the intercept. So let's see if we can get that second one. So now we're going to go through, right? We know that we want our line to be in slope-intercept form, so we want the equation of a line that's in the form y equals mx plus b. So we start off with our y equals mx plus b form. We know that m is our slope here. Well, we already know the slope. We just calculated that up here. It's 60 miles per hour. So we go ahead and plug in the 60. All right, so we know we're looking at y equals 60x plus b. Now we have to figure out what that b is. So what do? Well, we take the data from one of our points and we plug that in. So if you go back up here, we have 2 points to choose from. It does not matter which one you pick, right? It doesn't make any difference. I just picked the second one. So I've got an x value here and a y value here, and we just plug those in. So my y became 105, the y value from my point. and the x became a 2. That's the x value for my point, right? And you can see right here, my line y equals 60x minus 15 is going right through the 2 points in question, so we know we didn't make any mistakes. Okay, so that's how you find the equation of a secant line. Remember, a secant line is when we know 2 points on the line, right? So we have some curve here, this purple curve. We picked 2 points on that curve, and we found the equation of the line through it. That's a secant line. We're going to talk about something called a tangent line in just a moment. It's a little bit different. So you want to know the difference between a secant line and a tangent line because they represent different things. All right, so let's examine a new problem here for a second. So we have a new curve. So this is just the function y equals x squared. And I've got a point that I'm concerned about, the point 1, 1. So that's what this blue point is right here. This is 1, 1 right here. Okay, that's 1, 1. So notice that things are kind of fixed there. And then we're concerned about secant lines where one of the points is this point 1, 1. So you can see that black point is moving. That's because we're adjusting what the other point in our secant line is. You can see as that second point moves further and further away from our original point, the line that goes through those 2 points acts less and less like the original function. So see how right now that orange line isn't a very good approximation for the original graph. But as that point comes in and they get closer, it's getting better and better. And then boom, right when they get really close together, we get a line that looks like this purple one. This purple line is what we call a tangent line. It comes in and touches the graph just right at one point. It's only touching the graph right here at this point, and it's not crossing it, right? We can cross a curve by just drawing a line like across it like that, but that's not what we're trying to capture this behavior. We want a line that comes in really close and looks almost like it becomes the curve and then only touches at one point and then keeps going. That's what we're after here. So notice that as we take the 2 points on our secant line and put them closer and closer together, that secant line begins to look like our tangent line. In fact, we could say that as the points get closer together, our secant line approaches or approximates the tangent line, the purple one, right? So if you can kind of stare at this animation that's going on here for a few minutes and make sense of it in your head, this whole chapter is going to be a lot easier. So this idea of taking a secant line, squeezing the 2 points together, and that is a better approximation for our average rate of change over those periods. That leads us to our tangent line. This makes sense in the problem that we were working on a moment ago about the velocities of the vehicle. Because if you think about it, if you're driving on the freeway and you take a measurement at the beginning of an hour and you take the measurement at the end of an hour, that can give you the average speed that you did over that entire period, but it doesn't tell you a whole lot about any given instance, because someone could say, well, what was your speed halfway through? Well, who knows? Maybe you were stuck in traffic halfway through and you were barely moving. Or maybe no one was on the road and you were going 80 miles an hour at that point. There's lots of things that can happen inside of an hour, which means that your actual speed at any given instant may be very different than the average rate of speed that we found by calculating the secant line. Okay, so the whole idea in calculus is that we're going to take those 2 data points and squeeze them together, because we just said, well, knowing 2 data points isn't going to tell me much about my speed over the course of an hour. Okay, well, what if we shrunk that down to a minute? What if we took the what if we took our measurements at the beginning and ending of a 1 minute interval? That's probably going to give us a more accurate understanding of what our speed was over the course of that minute. But a minute is still a long time when you're driving an automobile, right? Maybe you're going, it's open roads for the first 30 seconds, and then at the last 30 seconds, you had to slow down because there was a slowdown on the freeway or something. Okay, so what if we just then went even smaller? What if we took our measurements over the interval of a second? Right? Well, unless you're just slamming on the brakes, your speed isn't going to change a whole lot in the course of a second for most vehicles and most driving. So if we take the average rate of change over 1 second, that's probably going to give us a pretty good understanding of what your speed was at that second. What if we now take an interval of 1/1000th of a second? Right? So over 1/1000th of a second, we have 2 measurements. That's basically going to give you your speed, because your speed can't change very much over 1/1000th of a second. So that's what we're doing here in this picture. We're taking the period of time over which we are measuring, and we're shrinking it closer and closer together. And as we do that, that gives us a more and more accurate representation of what your speed was in that exact instant. So we have this idea of a secant line is giving us an average speed over a period of time. That tangent line is giving us the instantaneous speed. So at that instant, what was your speed? And we can see here, we can use those secant lines to approximate our tangent line, right? So that's a major part of the calculus. So if you can kind of understand conceptually what's happening here, it's gonna be much easier for you what we're doing in the next the next chapters. So we're taking this idea of a secant line, which gives us an average rate of change. We're pushing those values for our secant line closer and closer together, which is going to tell us about the tangent line, which gives us an instantaneous rate of change.